Will Lyon, Developer Relations at Wherobots. I'm really pleased to have you on the show after attending the GeoParquet meetup in San Francisco about 3 weeks ago, where I met some Wherobots staff, including the CEO, Mo. So yeah, really happy to have you on and to get going with this conversation.
Great. Yeah. Thanks for hosting.
Okay, so let's get straight into it then. What's the elevator pitch for Wherobots?
So Wherobots is the spatial intelligence cloud. We build a platform that enables data practitioners to build geospatial data products or find insights in spatial data at massive planetary scale. We do this by building on top of Apache Sedona. Apache Sedona is an open source project that adds spatial functionality to distributed compute frameworks. So we leverage the power of Sedona in our Wherobots cloud service to not only manage the infrastructure that's required for running and operating something like Sedona at scale, but we also build on top of Sedona to offer a more cloud-native developer experience and also additional functionality that we can provide as part of Wherobots Cloud. And so, for example, we can provide a sort of spatial lakehouse experience, and we can talk more about what that means in a minute, but leveraging SQL and working with tables as the abstraction that improves the developer experience, but also additional functionality for things like applying machine learning models to satellite and aerial imagery, distributed vector tile generation, things like this. And the main interface for working with Wherobots is either spatial SQL. So this is the familiar SQL if you're familiar with tools like PostGIS, or also you can work with Wherobots through a Python API. So if you're more familiar with sort of the data frame API and approach of working with data that way. So that's Wherobots in a nutshell.
Awesome. I've got all sorts of visions in my mind about making it easier to set up planet scale geospatial services like Google Maps and things like that, so that you don't have to have the company like Google behind you just to even think about that. Okay, so I thought we could do some jargon busting. You've mentioned a few interesting terms there. So could you expand a bit on what a lakehouse is?
Yeah, so lakehouse, or in our context, we're talking about this idea of a spatial data lakehouse. So lakehouse is, I guess, a portmanteau of the words data lake and data warehouse. And so in a data lake is, the way I think of it, is really just a collection of semi-structured files. So this can be, in the geospatial world, things like, maybe GeoParquet files, raster images, shape files, GeoJSON, right? Like some things that have a schema, some things that don't, vector, raster data as well. In the data warehouse side of this, we're working with structured data. So we have a schema, we have typically SQL tables that we're working with, and so we can write SQL queries of a data warehouse. We typically have a shorter time to answering our questions there because we have that schema and structure applied. So the abstraction of a data warehouse that we're working with is like SQL tables. The abstraction for data lake is files. We have to figure out how to apply like a schema on read to these files, do some processing before we can start to leverage that data. And so the idea of the lake house is really to provide this familiar SQL table experience of the data warehouse on top of a data lake, so on top of a collection of files. And in the traditional data engineering world, that would be like a group of Parquet files with some metadata, and then there's a really interesting movement now to support these open table formats like Apache Iceberg. And so Apache Iceberg then becomes this layer that we expose SQL tables to the end user. So I don't have to think about how do I, partition my group of Parquet files. Instead, I just have familiar tables. I can write to these tables using SQL rather than having to like create new Parquet files in my data lake. That's the idea of Lakehouse. The spatial data lakehouse now adds native spatial types so that I can think of if we're working with vector data, points, line, polygons. I don't have to like construct these types. I can use spatial SQL. So I have these like ST functions for working with vector data or raster data. And in Wherobots, we do this by extending the functionality of Apache Iceberg, this open table format. We call this Havasu, but we're also working to add this functionality natively to Iceberg. So under the hood, this looks more like working with something like GeoParquet that has the all the functionality that we need for not only working with spatial types, but also performant functionality. So we can do things like spatial filter pushdown to do efficient, like spatial range queries, spatial joins, these sorts of things. But at the format that the end user is working with is this idea of a table. You don't have to think about how to partition these like Parquet files behind the scenes.
I have to confess I'm a bit of a deer in the headlights, but at the same time, I'm really happy to be hearing about all the concepts and ideas and frameworks and structures that are necessary for planet scale analytics and distributed computing systems that can achieve prompt responses for very large data sets. So yeah, I think I am performing a service to the audience of the podcast, but I do have to confess that a lot of this is the first time I've come across these concepts.
And it sounds quite complex because there's quite a lot going on there. But I think really like a big part of our goal at Wherobots, when I say to improve the like developer experience around that, is to abstract away a lot of those concepts. And so the interface that you have for working with spatial data lakehouse is SQL tables. You don't have to think about behind the scenes. This is a bunch of Parquet files stored in S3 somewhere. You don't have to think about how that's partitioned and optimized. Like the goal of Wherobots Cloud is to provide you a much simpler, familiar SQL table interface, but still with all of this additional geospatial functionality.
Okay. All right. So continuing on with the jargon busting, what's spatial ETL?
Yeah, so ETL is this process. It stands for extract, transform, load, where we're typically going out and we typically do these as batch operations. Maybe this is like daily, weekly, hourly, whatever, where we're going out to some system or multiple systems, grabbing a data set that may be in one format, maybe joining it with another data set, doing some aggregations, maybe writing this to a database, writing it to a new table format. In the geospatial world, spatial ETL adds some interesting components to that. One is this idea of working with spatial data types. So in the geospatial world, this might be something like grabbing a parcel data set and with parcel boundaries, and maybe a raster data set that has something like a weather forecast or a flood model, something like this. Doing a spatial join, maybe some sort of zonal statistics operation, and then writing that either to a table or generating some sort of new file format that we can then feed on to some other process. And this, I think, is pretty core to what a lot of our users do with Apache Sedona and Wherobots, where they have some piece of a data pipeline that involves some geospatial operations, and again at large scale, so at sort of national or planetary scale, and they want to sort of run these continuously as part of their data pipeline.
Yep, cool. All right, and last of all, you already in a sentence or in a phrase summarize what Apache Sedona is. Maybe if I could try to summarize myself and you could just check if you like. So there are distributed computing systems or infrastructure. My understanding of Apache Sedona is simply it's an open source solution that adds geospatial functions to that. Is that right?
Yeah, I think that's a good high level description. Maybe just to add a little bit to that. So when we're talking about distributed compute, we're talking about being able to leverage like a cluster of computers. You can think of like, I don't know, a serverless type of environment where we don't actually like have to think about this. We don't want to think about, okay, there's a huge cluster of machines that are breaking down my processing task into, hundreds or thousands of operations and running those in parallel and then either writing back to some distributed file format or sending me the aggregation back to my Python program. We don't really want to think about that. We just want to think of sort of the higher level abstraction, again, like either by defining a SQL query or something like that. And so adding Apache Sedona adds this geospatial functionality to distributed compute frameworks like Apache Spark or Flink or Snowflake. You can run this in Databricks, AWS services as well. And the functionality component, I think, is important, right? So we talked about adding these like spatial SQL ST functions that allow us to work with vector data, with raster data as well, to do things like spatial joins.
I'm glad you mentioned raster data.
These sorts of things. And then we can definitely talk a lot more about that. But I think also important to not just the functionality is the optimizations behind the scenes.
Yeah.
And this is a real core component to both Sedona and Wherobots, that there's a lot of interesting things about spatial and geospatial data that are, I guess, require particular implementations under the hood for efficient operations. And so there are some, cloud platforms that have some spatial functionality and some of these like spatial SQL functions for doing operations, but oftentimes the optimizations behind the scenes aren't really, a core part of the product. And so this is really important for Sedona to and Wherobots to leverage things like spatial indexing, spatial partitioning, generating query plans that can leverage spatial filters and spatial predicates, so that we're not only just have the functionality of doing these spatial operations like a large spatial join or a large spatial range query on a huge data set, but doing it efficiently and performantly. Because ultimately, when going back to this idea of spatial ETL, the more efficiently we can run these spatial ETL jobs as part of our pipeline, that's less computing resources that we're going to have to pay for. So that performance translates to, not just like, the time to run these, but the time that I'm paying for a large cluster of compute to be running. So that's another, I think, really important component. It's a lot of the behind the scenes things that we don't necessarily see in terms of functionality.
Okay, I'm going to try and keep the grin off my face, but I won't succeed, I don't think, for most of this session. I'm really excited because of, I guess, two things. Or at least what's coming up for me is a couple of perspectives on, I guess, roles in our industry and how they might be responding to the system that you're putting forward. The first one that comes up for me is like, imagine a global consultancy, I don't know, Accenture, for example. And I've never met their geospatial lead, but it makes me wonder if the kind of system you're talking about could be of interest to a consultancy that has to operate at a global scale, that probably tries to systematically consume and store in its own systems the spatial data that's issued by many or most world governments, and tries to sort of, as soon as they're updated at the source, respond in their internal system. Before long, that kind of a geospatial system will contain a hell of a lot of data. Would it be an idea for Wherobots to try to sell to that kind of a geospatial team leader and respond or replace whatever system they've cobbled together?
Yeah, that sounds like a perfect use case for Wherobots. I think there are a few, I guess, like components and requirements that make sense for leveraging the advantages of Wherobots and and Apache Sedona as well. And I think really it comes down to this scale aspect, and also the performance aspect. And so that's really what Sedona and Wherobots is optimizing for, is being able to work with large scale geospatial data. And so what's interesting is that this can be organizations like large enterprises that, because of the footprint of where they operate throughout the world, they have large scale data problems. But it's also not just large enterprises. It can also be smaller teams and smaller enterprises that are working with large scale data as part of creating, I'd say, like geospatial data products. And so this has been one thing that's a bit surprising to me, is that we're seeing like some interest from maybe smaller startups or organizations that create and publish geospatial data sets at planet scale, at national scale, and because of this, so things like you mentioned with maybe government administrative boundaries or parcel data changing quite frequently, and
parcel data is a big one. Yeah,
totally. And so being able to combine other data sets alongside that to create their geospatial data products is a common use case.
Yeah. Okay. So another one that comes up is another guest, Zan Fredericks. She was a liaison officer for the national map at USGS. And a really nice stat that she came up with was, I think that for every person in the US, the LiDAR data set of terrain means that each person gets 280,000 odd LiDAR points. So that's a nice illustration of the sheer volume of just terrain data that they have. So would it be another potential client in your view, at least to try to sell, what can I say, a higher capacity computing platform to the likes of the USGS to underpin something like the national map?
Possibly. I think leveraging that data to combine with other data sets, or to combine into some data pipeline, I think would be a really good use case. So perhaps being able to understand terrain and elevation as part of, I don't know, maybe like flood risk modeling, or things like this, I think could be, and doing this at scale, right? So like imagine that you're an insurance company, and you have an understanding of your portfolio, right? We can understand, like, here are all the parcels, and we can join that with maybe like building footprint data to understand the buildings on each parcel, and then we can combine that with either raster data that is maybe like a flood model, a flood risk model, or perhaps terrain data, slope elevation, like functions into that as well. I think that could be a good use case.
Yeah, and in terms of scale, last count, at least that I'm aware of, was that I think the Microsoft building footprints data set was of the order of 266 million polygons across North and South America, some countries in Africa and Oceania. So yeah, in terms of getting a feel for the kinds of data sets that Wherobots aims to give its clients comfort in dealing with. Okay, all right. So I think we're there in terms of the next question. What exactly is the niche that you're dominating? Can you give us a feel perhaps for some competitors?
Yeah, I think the niche that we dominate really is this idea of large scale geospatial ETL. And so there's a good chance that if you are building these sort of large scale planetary sized geospatial data products, that you are using Sedona, or have evaluated Apache Sedona, or Wherobots to sort of make this a lot more efficient process. And I think this makes a lot of sense if you think about kind of how the geospatial data tooling evolved. There's sort of the like desktop GIS tooling that a lot of folks are familiar with, like the Esri like ARC tooling, QGIS, the sort of tooling. Then in the open source, say like the Python ecosystem, things like GeoPandas, also in the open source world, like PostGIS, I think is a common tool that folks are using, and PostGIS is great. It has amazing functionality. The design of PostGIS, though, is that it's an extension to a transactional relational database, Postgres, right? And I think what we see from a lot of users is they've implemented some data pipeline using more traditional geospatial tooling. PostGIS, is certainly a common one, and they run into scale issues at some points. Either their data pipelines are taking too long, or they're having difficulty like running what they need to on a single machine, which is sort of the architecture of PostGIS and Postgres.
Yep.
And so that leads them to sort of look at more cloud native distributed compute tooling, either with something like a cloud data warehouse, so tools like BigQuery, Redshift, these sorts of things. And I think what we find there is that those cloud data warehouse tools are really optimized for working with large scale data. There are a lot of like Spark based tools as well. The cloud platforms built on top of that give us this functionality of working with massive data, but don't really have optimizations for working with geospatial data. Either they don't support a lot of the complex types or operations, or they maybe don't have some of those optimizations behind the scenes, and so they run into performance issues, with these cloud data warehouse tools. For a lot of these tools, they either have, the limited support for geospatial, either in terms of like types, operations, functionality, and then also lack of those sort of optimizations behind the scenes for things like supporting geospatial indexing, which with I think a lot of your listeners will be familiar with some of the challenges of geospatial data as compared to more traditional data sets, where the indexing systems that we use are typically much different. Geospatial data is by its nature multidimensional, so a lot of the familiar like database indexes don't typically provide much benefit when we're talking about geospatial data. But that I think is the gap that Sedona and Wherobots addresses, is sort of bringing the cloud native distributed compute functionality to the geospatial world.
Yep. Okay. So is there a single competitor that does this, specifically attaching geospatial, making geospatial easier to do in a distributed architecture or using cloud infrastructure?
I would say that I think the closest competitors are the types of cloud systems that we talked about, that are operated by say like Google, AWS, these sorts of systems that
all of those do have spatial queries that you can run. I know that from deciding whether or not to include, for example, AWS, even Alibaba Cloud in the Geospatial Index. I did check at least that they come with some out-of-the-box geospatial processing.
Absolutely, and they certainly do, and for I guess some level of scale and complexity, I think users have great experience with those working with geospatial data. But it's really when you get to the very specific functionality that you're looking for, or either these sort of large scale spatial operations like spatial joins and range queries as part of your data pipeline, that you can really see performance differences with tools that are optimized and sort of built, from the ground up to optimize for spatial versus tools that are not. And we do internal benchmarks against all of these tools. And in most cases, we find that Wherobots and Sedona are an order of magnitude or more faster than some of these tools when we're looking at very large workloads. And some of them are unable to sort of even handle the scale of what we're looking at.
Yep. Yeah, I remember looking at a table where time to solve was like 5 milliseconds or something for Wherobots, and of the order of 60, or as you said, order of magnitude higher for competitors. Although you had a comparison with memory load or usage, I don't know what the correct way is to describe that. And one of the comparisons was with Hadoop, and it looked like that was actually the memory footprint was lower. Do you have any comments about that?
Yeah, I'm not sure what benchmark that was, and I don't
Okay,
have a lot of
I've sprung this on
familiarity
you.
working with working with Hadoop. I think a lot of the comparisons are, I guess I would say the two different types of comparisons you would want to look at are looking at Sedona and Wherobots compared to other cloud services, but also keeping in mind that a lot of our users are moving from say like more of these traditional geospatial tooling like the PostGIS or like GeoPandas type workflow.
Yep.
So I think that's also like a relevant benchmark to think about, and also considering like the familiarity that users have of working with tools like PostGIS and GeoPandas, these things that are optimized for geospatial, and really transitioning from like tools that may not operate at the scale that you want, but that have sort of focus on geospatial to Sedona and Wherobots that are also focused on geospatial can be an easier transition than moving to systems that don't have that focus. So I think that's also an important aspect to consider.
Okay, sorry, I was having a grin on my face again because something that because this is called the Geospatial Index and there's about the 350 odd geospatial companies on public markets worldwide. Inevitably, there's many different sorts of areas that I'm doing interviews in. And one set is like Felt, GIS Carta, ArcGIS Online, all of the web mapping services. And an idea that came from all of those discussions was sort of a league table or some sort of a competition to sort of try to put all of those in a hierarchy. And I just thought maybe we should have some sort of a shootout with Wherobots and all the other cloud computing systems. Yeah, but I'll have to come up with a decent test with some reasonably heavy duty data sets. Yeah.
Sure. Yeah, and I think one thing to keep in mind, like we talked about, the like performance aspect of some of these operations, but also I think things like being able to work with both vector and raster data together, and we can talk about some of the like optimizations that we have for working with raster data. That's part of the storage layer and part of Wherobots as well. So that would be I think an interesting comparison to consider as we're talking about some of these other cloud services, ensuring that we're looking at like the full scope and the type of functionality that we have when we're working with geospatial focused data.
I guess I'll bite. So does Wherobots allow SQL-based raster analyses?
Yes.
Awesome.
Yeah. So we have, I want to say something like 90 plus raster SQL functions.
Awesome.
And there are, there are a few categories, I guess, of the things that we can do with raster data in spatial SQL and Wherobots. And these are things like, transformations, we're loading and working with raster data. And then we have, things like map algebra. So if I want to be able to do operations on, at the cell level across multiple rasters, maybe I want to calculate like, difference in temperature across, 2 years of data, something like this. And then one thing that is really interesting that we support as well with raster data is raster inference. So being able to run machine learning models on satellite and aerial imagery to identify objects, to do segmentation, classification. Essentially where we're going from raster data to give me the polygons of all of the solar farms that you've identified.
So this is like imagery. Segment anything from Facebook or Meta, I should say.
So we we launched this feature fairly recently in our last release, so it's still a bit early days. What we support now are a handful of models that we've adapted specifically to run in Wherobots. The goal is to provide like a bring your own model where folks will be able to bring models that they've trained and run those at scale
Yeah.
on Wherobots.
Awesome. Okay, so that's, I guess, the power of Wherobots is simply to get to an answer faster.
Yeah,
Yeah.
right. And to, I think going
Or
back
more cheaply.
to totally, I think going back to some of like the core principles, one is like to improve this developer experience. So being able to run raster inference using SQL, I think is really interesting. I haven't really seen that done anywhere else, and that provides like a very simple interface for what can be a very complicated task, and then also to do that at scale performantly, which translates to cheaper in the long run, because I'm running my cloud computing resources for less time.
About raster analyses and vector data, you can go between the two. And this, I guess, brings up a thread that I was mentioning before we started the chat, which is country scale analyses or constraints analyses to facilitate the emergence of high-speed rail in the US, or any really nation scale backbone infrastructure, linear infrastructure. So before you get to the point of deriving some sort of least cost path or least cost network, you have to have a cost surface, which we typically expressed in a raster as like a heat map or a cost surface. So I'm wondering if you would mind speaking to how a consultant confronted with the intimidating task of taking a country's environmental and social constraints data sets expressed in vector data, converting those efficiently into, say, a 10-meter cell size constraints raster. Is that something you would envisage a potential client using Wherobots to do?
Perhaps I'll admit that is maybe a bit out of the depth of my experience.
Sorry to spring something else on you out of the blue.
No worries. I will say that the components of doing that are there. Being able to work with vector data and raster data at scale, and I think that Wherobots supports functionality to do that using SQL. I think someone a bit more knowledgeable in the specifics of how you would go about that.
So could you do that analysis of, say you've got like, I don't know, the nation's rivers data set. And to convert all of these, a part of getting to the cost surface is to convert at the agreed cell size. So, for example, 10 meters. So your river lines turn into contiguous cells, strings of cells. Is there a function to rasterize vector data, or to go from line data to raster data?
I want to say yes. I have not done that myself, so definitely would want to double check on that. I know, that's a common use case. So I want to say yes, that's supported by our Wherobots in Sedona, but would have to double check on the specifics of that.
Okay, yeah. I really am putting you on the spot. It's partly because honestly, I'm really excited actually by the potential to really illustrate the power of geospatial and how we can answer big questions. And to me, one of the easiest ways to sort of wow people would be to do this nation scale constraints assessment, and sort of step through it all on YouTube in a series of videos. And yeah, not at all to sort of to flatter you, but to do this with a system like Wherobots. It would be a nice illustration, perhaps, of the power of it.
Yeah, and one of my a part of my job is, trying to identify what are a lot of these geospatial problems that folks are trying to solve. And I don't necessarily have like a super deep background in the geospatial area. Worked for database companies and as more of a full stack engineer in the past. I have some familiarity working with spatial data, but I think this has been one of the interesting aspects for me is to learn a lot more specifically about the geospatial aspect and to find what are the problems that folks are trying to solve, and then figuring out how to do that, and putting together exactly as you say, like tutorials, demos that can demonstrate how to do that sort of functionality. So I'm always on the lookout for problems that folks have that are at a large scale geospatial component.
Yeah, I mean, just speaking from my own experience, and I think if I can put it this way without divulging too much, but at least to divulge enough that makes it meaningful. From my experience, I can say for a country that's the size of 209,000 square kilometers, with 50 constraints data sets that needed rasterizing at a 25-meter cell size, using Citrix as infrastructure, just a single sort of virtual workstation, if you like, in Citrix. It took of the order of 6 hours to go from those vector constraints data sets to a single raster constraint surface. So if you scale that up to a country that's significantly larger than 209,000 square kilometers, the US, that's definitely where you're going to give up using that particular computing solution. So yeah, anyway, it's bringing into focus for me in using my consulting experience, the value of this. Anyway,
Great,
cool.
Great.
So just, I guess, to round out the business aspects of Wherobots. So what is the skin in the game of the owners or owner management and staff? And by that, I mean like part ownership really of the company, if any.
Yeah, so Wherobots is a venture-funded startup, based in San Francisco and Seattle. Wherobots is founded by the original creators of Apache Sedona. So our CEO, Mo Sarwat, and our chief architect, Jia Yu, are the original creators of Apache Sedona. And the team at Wherobots is pretty amazing. We have, on the geospatial side, we have some of the core committers and maintainers of Sedona and other folks with experience working with large scale geospatial tooling. On sort of the cloud platform side, we have engineers who have worked at as data engineers or data infrastructure for some of the largest companies at high scale. So the team, I think, is really impressive. In terms of sort of skin in the game, our co-founders come from academia at Arizona State University and a database computing lab where Apache Sedona was created, and based on the success of Sedona, decided to leave that world and move into the venture-backed startup ecosystem.
I remember hearing a bit of Mo's backstory over beers in SF. That was good.
Right. Yeah.
Cool. So maybe this is private, but is there an aspect of the incentivization of staff through part ownership of the business, or at what level? I assume Mo is a part owner somehow, or is it that your venture backing are 100% owners and nobody who works for Wherobots gets any ownership? Just trying to understand the incentivization. Yeah.
Yeah. So the way, I'll say that the way it typically works in venture-backed startups is the founders maintain a large percentage of ownership, and each round of financing, a little piece is taken by the VCs.
Yeah. And
as a VC, you typically don't want to take too big of a chunk of the company, because then if you leave nothing left for the founders and employees, then they're not sort of incentivized to to work as hard and build amazing products. And I think, VCs typically want their incentives aligned with the founders. And then when it comes to the staff and employees, typically in VC-backed startups, there's an employee option pool, because again, the founders want their incentives to be aligned with those of the employees as well, and to sort of have long-term incentives aligned, not just for working for a paycheck, but also like building something together. And I think that incentive structure is pretty common in so the VC back startup ecosystem that I think is commonly replicated, and I think leads to success in a lot of cases, at least of sort of unifying the team and having a vision for what we're all building and building it together. And that I think makes it a lot more fun and a lot more exciting when we all kind of have that that shared goal that we're working towards.
Yeah, we started to address the idea of who your ideal customer is, but let's at least just directly address that. So in the minds of Wherobots, who are you aiming to sell to ultimately or most frequently? And how do you always ensure that you're working backwards from the needs of that ideal customer?
Yeah, so we talked about this, I guess, a little bit at the beginning, where we say that we're enabling data practitioners to build geospatial data products or to find insights in large-scale data. And so I think what that means is, groups that are working with massive amounts of data to build these geospatial data products as part of a pipeline that they're running regularly. And so as an example, I think a lot of users will be familiar, or a lot of listeners will be familiar with the Overture Maps Foundation. So Overture Maps Foundation, they create public data sets, things like points of interest, admin boundaries, building footprints, that they combine from multiple data sets and then make freely available. And Overture Maps Foundation uses Apache Sedona as part of their data preparation pipeline. They do this in a few different ways, but one of the things that they do, and we actually co-authored a blog post with one of the engineers from Overture Maps Foundation that talks about how they use Sedona to generate GeoParquet, and how they use sort of a dual indexing strategy to do that. So anyway, that I think is one good example of kind of the ideal customer, is a group that has a regular recurring sort of data pipeline process for building geospatial data products at planetary scale. And the other part of that, as I mentioned earlier, are sort of organizations that, because of the footprint of their operations, that they have very large scale spatial needs. So a good example here would be Land O'Lakes. They use Apache Sedona to generate sort of custom.
Hang on, Land O'Lakes, that reminds me of a place in Florida, or is that totally unrelated?
Perhaps. They operate a lot of farmland throughout the U.S. and so they have lots of like farm parcel data, and they want to be able to generate custom water quality and weather predictions for these farm parcels. And they gave a talk at the Data and AI Summit, talking about sort of how they do this. So I think to answer the other part of your question is, how do we work backwards from their needs? And I think the answer to that is largely with a focus on scalability. So the ensuring, as we're adding features, we're interested in not just the functionality, but also, does this work at scale, and is this extremely efficient? So can we do these operations efficiently at planetary scale? So for example, the raster inference functionality.
As an organizational goal that you've got that as the benchmark, I just want to say.
Right. I mean, that's I think the things like functionality, like, can I do this? These are kind of the table stakes, but what our customers are really interested in is, can I do this at scale, faster than other other tools? So for example, the raster inference functionality, when we add this, it's important that we benchmark that at extremely large scale, and comparing this to other approaches as well.
So Land O'Lakes, did you say, was trying to predict the weather or climate at within land parcels? Did I summarize that at all correctly?
Yeah, so they in this presentation they gave at Data and AI Summit goes into a lot more details on this and how they do that. Basically, what they're doing is they're taking their farm parcel data and water quality raster data and weather and climate prediction data, and essentially doing like joining those together, doing some sort of zonal statistic operations, I guess, on that.
Okay. Yeah. The reason
and then what they do is they use that as part of their pipeline to then generate reports for I guess the operators of these specific farms to make plans for
summarize
for farming operations.
Opportunity. Yep. The reason why I want to return back to that briefly was there's another thread. I find myself in all of these episodes talking about the different threads that are going through them all. So one that's more frequent lately being discussed in episodes is natural capital assessment, the concept of nature as an asset class, biodiversity, related carbon metrics assessments, things like that, and all of the UN assessment frameworks that relate to that. These were nicely discussed in the last episode with Flint Pro, but it's a thread that started with Gillian Malod, who used to work for MSCI. Spatial risk systems that also related to that. And there's a few others that I've forgotten. Anyway, at least what came up with Flint Pro was that they also do planet scale analytics. They have clients all around the world. They're about integrating a bunch of different remote sensing derived metrics, I can say, and aggregating them at the farm level or the parcel level. So yeah, it seems that this system, you have an example there already of a natural capital related kind of client, and it does seem that your system can be unleashed on this natural capital emerging sort of space in the application of geospatial.
Yeah, that sounds like a good use case for Wherobots. I'm aware of maybe not in this maybe not in this specific area, but certainly the types of solving the types of technical challenges that are involved in that. I'm aware of folks applying that, and I think that this is a good opportunity to point out that like at Wherobots, like we don't want to sort of build and sell these sort of aggregated data products. We want to provide the platform that enables other folks to build those.
You're not about the domain specific solutions, but enabling them. Yep. Cool.
Exactly.
All right. Talking about metrics, some sort of metric of my enthusiasm, or at least how interesting this is to me, is we've gotten almost through we're through the time booked and we haven't gotten to the end. Do you have time to continue, or do you need to go about your day?
No, I'm good. Yeah, happy to keep going.
Cool. Okay, awesome. So we've talked about your ideal customer, how you work backward from their needs. Next up, I guess, is some sort of indication of your success there. How fast and sticky is growth?
Yeah, so in the open source world with Apache Sedona, I think we've seen really good adoption there, and also a good way to measure success of an open source project is contributors as well, and so we have I think hundreds of contributors and users from large companies. But in terms of usage of the open source product, I think we now have over 1.5 million downloads per month of Apache Sedona, and we've surpassed over 30 million downloads since launching Sedona. So that I think is a great indication that there's lots of interest and demand for this type of tooling on the Wherobots Cloud platform. Wherobots Cloud is a bit newer than Apache Sedona. Apache Sedona, the early pieces of the project started around 2016, 2017. So that's been able to grow in adoption and mature over time. With Wherobots Cloud, we launched in October of last year, and so what we see there, we launched with a free tier, so anyone can sign up for Wherobots Cloud and create an account and have sort of a base level of resources available to do this type of analysis in a Jupyter Notebook environment.
Yep.
And what we've seen there is, a lot of users trying out the free tier, and sort of kicking the tires there, going through some tutorials for usage there. And then, of course, I think we're seeing a lot of interest of folks that are running their proof of concept and sort of the free tier and upgrading to the professional tier, which gives you more resources, so you can create larger clusters to solve larger spatial problems, or folks that are familiar with using Sedona and have used it in the past but don't want to maintain their own infrastructure of running Sedona at scale, and are interested in adopting Wherobots Cloud for sort of the managed service functionality.
Yep. How can people use Wherobots to assess and mitigate risk associated with man-made and natural events?
So I think we've talked around some of these ideas. I think the general, and I'm sure your listeners have a lot more domain expertise than me in some of these areas, but I think the general type of data that you use to address some of these problems are going to be raster data. And so for mitigating man-made risk, one thing I think is important is understanding the physical infrastructure and being able to derive that. And so we talked about this raster inference functionality. And so I think being able to identify things like offshore wind farms, which is one of the models that we've trained and made available in our initial raster inference offering, can be an important piece of going from sort of looking at satellite imagery to understanding what sort of infrastructure is there. And in the terms of sort of natural events, the type of raster data we would work with there, things like climate data. I worked on an example looking at combining aircraft data with weather data a bit ago. And so we were looking at deriving aircraft routes from ADS-B data. So going from point observation data to the actual sort of flight paths and routes that aircraft are taking.
So is that how the ADS-B data comes back? It's just a strings of points at time intervals?
Yeah, so ADS-B data is essentially telemetry, and so you have aircraft that are broadcasting at some interval point observation, along with additional information about like their heading, elevation, speed, these sorts of things. And there are lots of interesting services that combine and sort of crowdsource ADS-B data, because it essentially comes from ground sensors that folks kind of collect and put together. And so going from that like point data to working with line strings was a piece of this analysis, and sort of aggregating that at the individual flight level to sort of derive the actual route that aircraft are taking over time. And then the question is, well, what are flights that have more frequent risk of disruption, by intersecting with areas that have frequently severe weather events, and so we can do sort of some spatial joins there to see where are we intersecting with weather events, or we also imported some Doppler weather radar, so we can see kind of in a more real-time format where are we potentially at risk, either at airports or flights that are in flight currently.
Yeah, to me, a good one there is schedule risk. And it's nice that you started to talk about, I guess, the fourth dimensional or time-based analysis or time series, because I guess you can inform the public, you can inform airlines themselves about, based on historical patterns and then weather predictions as well, how at risk a given route is for weather-based disruptions. I guess, is that what you're talking about?
Yeah, exactly. Yeah. Absolutely.
I again, it's really inspiring to hear about all these global scale analyses, because a lot of consultants, such as me, have spent their lives working on a very constrained, defined area in a small country. So yeah, it's nice to think big. So step us through the use of the platform to monitor assets in real time, manage a supply chain efficiently, and take accurate logistical decisions swiftly.
Yes. So for this one, what comes to mind is what I'm aware of one of our users is doing, and I don't know if this will address the complete question, but certainly a component of this, which is I think also representative of how users use our platform in the context of geospatial ETL, where oftentimes as part of our pipeline, we're transforming data from one format to another to feed into deeper analyses. So let's imagine that we collect a lot of telemetry data from either vehicles that we manage, maybe like a delivery service where we have lots of vehicles out running delivery routes, or we're collecting perhaps like telemetry data from individual drivers and these sorts of things. And that gives us, very similar to when we were talking about the ADS-B aircraft data, that gives us billions and trillions of point observations, points in time. But really, to do any sort of analysis for logistics or supply chain analysis, we need to understand the routes. I'm not just interested in the point observation. I'm interested in this delivery vehicle, what streets was it driving on at what time, and the route that it was taking. And this is a problem called map matching, or sort of where we're snapping to a grid. And this is one of the functionalities of Wherobots. I mentioned how the value add at Wherobots is managing, sort of the infrastructure where Apache Sedona can run, improving the efficiency and performance of Sedona, but also then building on top of Sedona to add additional functionality. And map matching is an example of that latter one, where we've added functionality in a Python package to do large scale map matching. And so in this case, our users are taking their telemetry data, and again, this can be billions and trillions of points observations every day, and essentially matching that to routes based on street grid information, either from OpenStreetMap or other providers. And then what they do is that gives them essentially like line string geometries from their point geometries, and then they're able to write that back to our spatial data lake table. And so rather than just having some like GeoJSON or GeoParquet file, they're actually able to update those tables with the day's routes, which they can then feed into other analyses and other systems.
So specifically, the day's routes will be expressed as segments from the network data set that you're map matching onto?
Yeah, so it would be, a row in this table would be one of the day's trips for one of your delivery drivers.
But that will be expressed as the subset of segments that your point returns from the delivery vehicle matched onto from the street network. If I'm even characterizing this?
Yeah, so it could be
in a way that you are.
Yeah, so it could be simplified as a line string geometry, or you can also
but sorry, the point is that it won't. Sorry to cut in. The point is that it won't be the set of connected points from the GPS that's mounted in the delivery truck. It will be that those points are matched to segments from the street network.
Exactly. Yeah. So rather than having sort of lossy information from GPS coordinates, your points are actual intersections in the street network.
Yeah, exactly. And then day to day, week to week, that makes the trips comparable across vehicles, and you can have analytics of growth in the network or growth in the services on the network that your logistics operator is providing.
Exactly. So you can then analyze those routes for efficiency. You can also see as the street network changes, right?
Yeah.
Any types of more critical analyses of that. Exactly.
That brings up all of the different sources of these incredibly heavy data sets. I mean, I remember after the chat, or actually in preparation for my chat with Zan Fredericks about the national map, I started downloading the national maps transport data set or road data set. I think it was of the order of 13 gigabytes just for the US. But there must be a whole bunch of private providers of those data sets too. Like I imagine you can just buy it from Google, Microsoft. You talked about the open source one. Yeah, it's fascinating. It brings up so many different avenues you can go to.
Yeah, and Overture Maps Foundation that we mentioned earlier also publishes transportation.
Do
they
they?
have a transportation theme that includes. I believe it comes from. I found the structure of it quite interesting, right? So there's segments and connectors,
Yep.
sort of as two different data sets, which I believe comes from kind of the way that TomTom internally represented a lot of their navigation data, which TomTom is a big component of Overture Maps Foundation.
Yep. And from what I understand, reading, I think, is it Tom Killick? At least his surname, I think, is Killick on LinkedIn. ETAC, which this guy was involved in. Apparently, TomTom is an evolution of ETAC back in the day, which was an early car-based navigation system.
Right. Those were the very bulky
Yeah.
hardware that was installed
Yeah.
in cars, right?
Yeah, and it was incredibly difficult to install because essentially it used dead reckoning. It didn't have a GPS, and it also had its own version of map matching because it had to essentially snap the vehicle's position that you obtained through dead reckoning and keep it snapped onto or matched onto the ETAC street network. Yeah,
Right.
so I hope I haven't totally butchered the description of James's amazing system. Okay, I keep getting too inspired and too excited to effectively work through this agenda. Okay, so the next one is how can you work with raster data using spatial SQL in Wherobots? We've touched on this. Maybe you want to briefly dispose of this question if you have an example.
Yeah, I guess one thing, we talked about spatial SQL functions that we can work with the vector and raster type together at large scale in Wherobots and Sedona, which I think is a real value add that we don't see that at scale in a lot of other systems. But I think one thing that that's interesting that I can add here that comes to mind is how this works behind the scenes for enabling some of the raster data functionality. And that's this idea of outDB raster. So with raster data, we have, sort of say like if we're talking about geotiffs, cloud optimized geotiffs, we have sort of the, actual band data, values for cells, but then we have the spatial metadata as well. So, what are the boundaries for this raster, SRID, these sorts of things. And so the outDB raster format allows us to store just the spatial metadata in our table, in our sort of storage format that we're working with. And the actual band data still stays stored on, say, like cloud storage if we're working with cloud optimized GeoTIFF. And so this allows us to do operations that leverage just the spatial metadata. So, like clipping, filtering, range queries, these sorts of things, allows us to do that very efficiently because we're not loading the actual band data from cloud optimized storage, and that's a lot less data that we have to move around and these sorts of things. So anyway, that's one of the I think core components when we get back to looking at how are we optimizing for performance. This is one feature that allows us to do that, to work with large raster data in Wherobots.
Great. Yeah, it is a nice illustration of the kind of attention to detail that a team like Wherobots that's focused on the geospatial aspect of computing in the cloud, the kind of attention you can give to solving all those little problems. Great.
Exactly. Yeah.
Okay. I do have one final question, but I wanted to shove one extra in if you've got the time.
Sure, of course.
So it's coming back to, I guess, this grand uh, demonstration of what geospatial can do in the context of an infrastructure problem that needs to be solved for the public good, in my view, in the US, which is to somehow provide momentum to high-speed rail emerging. So a basic one is the projections or the projection that you use for the data. And I started to sort of broach this subject with Zan, and we talked about the Albers conformal conic projection and others, where you have a single projection for the whole national data set. You've got to choose where the lines of latitude are that your cone will dig into the surface and come out the other side, if I can put it that way. And there's some choices that you have to make to essentially minimize distortion from having a national scale projection. Another way to do it is to break it up into the UTM zones. I don't know how many there are. I'm not an American, but there would be a few UTM zones that the US would span. So what do you have to say about a data set that is distributed across a number of zones? What might someone have to do? Is there anything that Wherobots can do to help account for this? And I realize I am putting you on the spot again.
Yeah, no worries. Yeah, so I guess like there are various trade-offs there, right? So the trade-off of having, one single projection that, we're trying to preserve area, I guess, in the case of Albers. But you are going to end up with, some distortion at, more extreme areas of the boundary. I guess I won't speak to how you choose to optimize and those trade-offs. I guess what I will say though is that as a platform optimized for working with spatial and geospatial data, that the way you would be able to work with data sets in multiple projections in Wherobots is basically you can explicitly set the SRID and reproject the data in your SQL statement. So if you're doing a spatial join or any spatial operation where we're working with data in different projections, different SRIDs, you can simply set the SRID for a common one when you do that spatial operation.
I mean, because like you could just go with a common one that probably a lot of people would start with is WS84 for a global data set. But if you go for example, GDA 2020 from Australia, this is actually quite an interesting datum where it's actually meant to reflect the fact that Australia is shifting, even if it's less than a centimeter, over a number of years, the position of Australia will shift in a noticeable degree. So, I mean, and it's almost like, it's the first thing that any sort of national survey agency will do for any national jurisdiction. They will come up with a nice, accurate projection for their. So, for example, it's British National Grid in the UK, where I am at the moment. So, it's just something that to me springs to mind to correct for, or it's a risk to take into account when you have planet scale analytics and how accurate they might be. So it sounds like there has been some thinking about that at Wherobots. But yeah, I just feel that it's something that I would appreciate some more, you expanding on more. And I don't know if it's within the scope of this chat, and probably there's a whole podcast that could be devoted to just this issue of positional inaccuracy.
It's a common problem, right? In the geospatial world. I think this would be a good one to dive deeper into. I think this would go in my category of learning the challenges that folks have in the geospatial world, and diving deeper into putting together some examples for how we can solve those in Wherobots. Yeah, that's a good one.
Okay, so for the upcoming shootout between all the cloud computing for geospatial platforms, we'll add that to the list.
Absolutely.
Cool. All right, so then the final one is, how are you fostering the growth of the next generation?
That's an interesting question. We could interpret in a few different ways. The thing that comes to mind for me, so Mo, our CEO, likes to say that at Wherobots we're building a brain and memory for the planet, and there are a few ways to interpret that as well. I think one is that it maps to the technology architecture, and in a cloud native technology architecture, you want to separate storage from compute, because you don't want to move a lot of data around. You want to sort of bring compute to the data, and so that's kind of one way to think about that. Is we have the brain, which is the compute for the planet, but then we also have the memory, which is the storage for the planet. And early on, I talked about some of the ways that we've optimized this idea of working with the spatial data lakehouse and leveraging some cloud native ideas and best practices in the geospatial world. So that's sort of the memory component as well. But I think really at a higher level, talking about building a brain and memory for the planet is really talking more so also about some of the challenges that we're trying to solve, and being able to, I think about a way that you can make sense of planetary scale information about our planet, and make that as simple and accessible to work with as possible, which I think sets up a lot of the infrastructure for some of the problems that the next generation needs to solve.
Yeah.
So take from that what you will, but that's kind of what comes to mind.
I love it because it relates again to this ongoing thread of natural capital assessments, related carbon assessments, and the concept of nature as an asset class, which means that the concept can be consumed by the financial community. So what you're saying also is meaningful to me in the context of the UN sustainability goals, where they require some spatial analyses for meaningful progress to occur. So there's a whole bunch of, I guess, issues meaningful to human survival that what you've said relate to. God, I don't feel like I was coherent there.
No, that makes a lot of sense, and I think it addresses a lot of the challenges that are coming up for the next generation for sure.
Cool. Okay. I also want to end things on a call out or a shout out to City Nerd, which is a YouTube channel that's becoming more and more popular lately. Why am I saying that? Well, I think there's of the order of 10 videos that he's done about ideal city pairs in the US to connect with high-speed rail. So I feel like this here and this discussion is an example of how it's going the next step of how the geospatial community and the infrastructure that it can harness, for example, what you're talking about, can be brought to bear on solving actually what the route could be between the city pairs that City Nerd is identifying. So yeah, I look forward to getting at least a trial version or the demo account for Wherobots, and yeah, kicking the tires and seeing what kind of cost surfaces can be derived from the constraints data sets that can be used to help characterize where we could send high-speed rail between those city pairs from City Nerd. So yeah, thanks. And also, yeah, thanks, Will, for getting on the chopping block today.
Yeah, absolutely. Thanks for inviting me. Thanks for hosting this podcast. And yeah, as I mentioned earlier, there's a free tier of Wherobots Cloud. Anyone can sign in and create an account. We have a series of example tutorials that you can walk through or bring in your own data to get started. So that, I think, if you're interested in any of the things we talked about today, that's the best place to go next is wherobots.com, and yeah, just create a free cloud account and kick the tires.
Yep, I'm definitely keen. I'd like to keep that thread going in through the next episode. So yeah, thanks, Will.
Great. Thanks a lot.